So building on the nebular theory, why do we have 4 inner rocky planets and then 4 outer gaseous planets? Well, let's look at our solar nebula. And remember, this was basically the nebula from which the sun gathered about, 98% of the mass of the nebula, and then the remaining 2% was distributed in planets. Not evenly, might I say. So the nebula consisted of hydrogen gas and helium gas. Now, one of the things we need to consider to make a planet is matter needs to condense. Now, you're probably familiar with like condensation you get on the outside of your glass of ice water, that sort of thing. So what's happening there is water vapor in the air, gas water is condensing to become a liquid. Okay, so when we talk about these condensation temperatures, we mean that the gas is condensing to be a liquid or a solid, I guess, would be the same thing. But hydrogen and helium will not condense in our nebula. But compounds containing hydrogen will condense if it's colder than 150 Kelvin. So hydrogen compounds include water, methane, and ammonia. So notice that 98% of our original solar nebula was hydrogen and helium, and that's not going to condense. And 1.4% of our original nebula was hydrogen-containing compounds, water, methane, and ammonia. Well, with regard to rock in our solar nebula, a couple of different things. Notice that rock will condense at a higher temperature. This means it doesn't have to be as cold as it needs to be in order for hydrogen compounds to condense. So it can still be pretty warm, and you can have rock that is going to go ahead and liquefy or solidify. But the percent in our original solar nebula was 0.4%. The last major ingredient of our solar nebula would just be individual elements, individual atoms of metals. And notice that metals, the condensation temperature, the temperature will go from being a gas to being liquid or maybe even solid, would be 1,000 to 1,600 Kelvin. So notice it can be pretty darn warm near the sun, and you're going to have these metals condensing out. But only 0.2% of your original solar nebula is made up of these metals. Now, just kind of, if you kind of look around or think of your everyday life and think of how many metals you have in objects that you use, and then think of this fact that our solar nebula, the thing that made our sun and the planets, was only 0.2%. I imagine that's by mass. Only 0.2% of our original solar system is metals. It's amazing. So that's kind of setting up for this idea of a thing called a frost line. So what we have here is this little blob here in the middle it's our proto-sun, which eventually is going to begin nuclear fusion in its core and eventually become a full-fledged star and be our sun. Right now it's a proto-sun. And we have a white line here called the frost line, but it's not your typical frost line. Inside the frost line, it is cool enough, it's still pretty warm, but from the frost line, closer to the sun anyway, it's cool enough to go ahead and have rocks and metals condense. So they won't be a gas. Rocks and metal will be either a liquid or a solid. Notice that here close to the sun are hydrogen compounds like H2O, methane, and ammonia will still be a gas. Okay? Beyond the frost line, so it's going to get cooler as you get farther from the proto-sun. Out here beyond the frost line, we're going to have our hydrogen compounds, being water, methane, and ammonia, go ahead and now they can come out of their gaseous state and go ahead and liquefy. Okay, so we end up with these two types of planets on either side of the frost line. We have terrestrial planets inside of the frost line, and then we have Jovian or gaseous planets beyond the frost line. Now I've heard recently this is actually kind of controversial, so I'm just going to kind of stick with what Bennett does in 2012 and explains our rocky or terrestrial planets and our Jovian or gaseous planets. So as we kind of look at either inside the frost line, look at these metals and rocks coming out of their gaseous state, or beyond the frost line when it gets even cooler, think of the hydrogen containing compounds of water, methane, and ammonia going ahead and coming out of a gaseous state. Keep in mind that those things I mentioned, the metal, the rock, and the hydrogen containing compounds, they only make up 2% by weight of the original solar nebula. The remaining 98% by weight of the nebula is hydrogen and helium gas, and it's not going to condense anywhere. But when we talk about the formation, or when we talk about how our Jovian planets kind of evolved to be what they are today, Jupiter, Saturn, Uranus, Neptune, what we're going to see is as they got massive enough, these gases, hydrogen and helium, actually the mass was great enough to go ahead and keep those gases associated with the planet. Okay, so we have a frost line. Inside the frost line, it's too hot for those hydrogen compounds to go ahead and condense. And that gives us our terrestrial planets. Outside the frost line, we can have those hydrogen-containing compounds condense, and we can go ahead and make these large gaseous planets. Okay, so formation of the terrestrial planets. Actually, both terrestrial planets and Jovian planets, I think of kind of making a snowball. Here in the Midwest, you know, if you get a nice heavy snowfall, you can enjoy going out and taking, starting with a little bit of snow and rolling it, and that snowball gets bigger and bigger and bigger, and you accumulate more and more snow as part of that snowball. And to me, the formation of planets kind of reminds me of that. So before it's a planet, it's a cute little thing called a planetesimal. Okay, planetesimals actually are kind of conglomerates of material that will glob together and get larger. So actually, I've heard recently that planetesimals, it's thought that it wasn't necessarily gravity, but electrostatic attraction that kind of get those particles getting together in the first place. But a gravity eventually kind of kicks in, and the planetesimals combine to form our terrestrial planets. So I thought this is a good little animation. I'm going to bring it up. On a recent recording, I know I talked about these protoplanetary disks, and we actually can see other nebula that are going to result in a central star, and around that central star are these, now it's not a star yet, it's like a protostar, but around this object that's going to be a star are these disks, and these are like what we call protoplanetary disks, because that's where that star is going to get, that's where planets are going to form. Okay. And remember, we use the word planetesimal as kind of like a little object that's not large enough to be a planet yet. We use the word accretion to describe kind of this snowballing effect where you take something small and ultimately gravity will make planetesimals join together to make one object that eventually will become a planet. And that process is called accretion. So let's see if this will work for me. Maybe. Oop. There it goes. So I mentioned the frost line, and actually the frost line here is kind of this, it's a kind of a light blue line, and this line here, I'll go ahead and the green line, let me go ahead and click there, and it says actually within that green line and towards the center of our proto-sun, or a protostar, it's too hot there for even even rock and metals to condense. So if we click here, let me go ahead and in this region, click this little animation. Hopefully you can see these little gray blobs. So these little gray blobs would be little condensed rock and metals that are finding each other, forming planetismals. Okay. Then let me go ahead and click a region outside the frost line. And now you see we have the gray, which represent the metals and rock, and then we have the blue now, which would represent those hydrogen-containing compounds like water, methane, and ammonia. So see, it's a different cat there. Okay, but again, planetismals and a process we call accretion. So this would be the protoplanetary disk. This would be the star not yet turned on. Excuse me. And you kind of see from left to right, letting time do its thing, where we get larger and larger planetismals. And eventually, the planets, what we say, clear their orbit. You see why that was kind of a significant, by definition, Pluto has not cleared its orbit of debris. And so you can kind of think of this process in planet formation, that these objects are large enough, they have cleared their orbit, and joined the materials joined together that was in their orbit, in a sense, to form the planets. Okay, so that was the inner planets, terrestrial planets. The Jovian planets, or the outer planets, are kind of similar, but remember now on the other side of the frost line, we can have condensation of these hydrogen-containing compounds like water, methane, and ammonia. And then, like I said, when these planetismals, or ultimately kind of the near end formation of a planet, gets large enough, its mass will exert gravitational force on hydrogen and helium gas, so that the force of gravity is so strong with, for instance, Jupiter, that even something as light as hydrogen and helium will stick around or be drawn to it. So let's take a look at this little animation. Okay, not a whole lot to see here. But remember when we were looking at the relative amounts, we said that by far our solar nebula mostly contained gaseous hydrogen and helium that was not going to condense. But the second most abundant ingredient in our solar nebula were these hydrogen-containing compounds. So that's kind of what you saw kind of snowball there. Okay. So one of the things about our Jovian planets, I don't know if you remember, but I said beginning with Jupiter, all four of those gaseous planets have a system of satellites. They have several moons that are in orbit about the planets. And as it turns out, actually during the formation process, each what was going to be a planet had its own kind of little accretion disk, or its own little disk where moons could go ahead and be formed. Isn't that interesting? Makes sense. Well, at some point, and we'll talk more about this when we talk about stars being born and we talk about our sun coming alive, but at some point in the center of our sun, it was hot enough in the sun's core and dense enough in the sun's core to go ahead and take hydrogen, squish it together, or make two hydrogen atoms fuse together and create a heavier helium atom and release a lot of energy. So of course what I'm describing is nuclear fusion. So the sun turned on kind of all of a sudden, I suppose. And our sun, when it turned on, just like any other star, created an outgoing positive pressure we call solar wind. So our sun is blowing in all directions. So what this animation does is it shows the four terrestrial planets Of course, we have Mercury, Venus, they're both white. Then the third one is the Earth, and then we have Mars over here. And we're going to see what happened. Can you kind of see the little bit of haze here? Think of that haze as kind of being kind of remnants of the solar nebula that didn't make it to become a planet or the sun. So here we go. I'm going to play that again. Okay, isn't that cool? So you see how the sun shrank, turned on, and you see those little yellow jags are the these little yellow jags right here is the solar wind, and you see how it cleared. Well, one way to look at it is cleared stuff. Planets couldn't get any bigger. Okay, basically, stuff that wasn't associated with a planet was kind of blown